Thanks.
It's running.
So good afternoon, everyone, to the webinar opening up the Cloud Edge Continuum to a new generation of applications, which has been or is being jointly organized by two EC projects, Physics and Charity. My name is Uwe Herzog. I'm the project coordinator of the Charity project, and I have the pleasure to moderate through this webinar. Both Physics and Charity are projects in the cloud area. They work together on the same challenge on challenges in the cloud domain, yet they complement nicely so that I think everyone watching the webinar can get some good idea of some of the challenges and progress of work in these areas. And I think both activities complement nicely each other. Before we move on, let's first take a look at the agenda for today. So I will start with a brief introduction to both projects. I will keep that short because then we have more time to go in the actual presentations, where we will start with two presentations from the Charity side. The first one, Tarek Taleb, will give an overview of the Charity project, and then colleagues from HPE, Paolo Barone, Marco Di Girolamo, Giovanni Giuliani will give an introduction to the application management framework and offer some demo. And then we will move on with Physics, again with an overview, which will be given by Fabrizio Di Peppo, who is the coordinator of the Physics project. And then following that, there will be also again an introduction and also a demo to the design environment in Physics. And this will be presented by George Colores. And then finally, at the end, we still have reserved some time for any potential question, and we will try to give the answer to that. If there are any questions already during the presentations, please put them in the chat. I will pick them up from there, and then we will collect them and answer them at the end. We will have the chance, of course, if there's any short, immediate question to any of the presentation that cannot wait until the end, then I think we have the chance to address them quickly as well. But the general idea is to have them at the very end. Okay, then let me give some quick overview of both projects. So Charity, full title is Cloud for Holography and Cross Reality. It's an EC-funded project, Horizon 2020, and Charity started in January last year and will run until June 2024. And the main objective of the project is to develop a complete framework for enabling immersive communication. So that's a focal point from the application side, immersive communication and services like virtual reality or holography. To support day-to-day business operations, social events, and general lifestyle. So we are not having just commercial customers in focus, but also the growing number of private customers to which we hope the services will become available in the upcoming time. In order to achieve that technically, we will leverage, or we do leverage, an innovative cloud architecture that exploits edge solution, which is an important aspect in our concept. A computing and network continuum, autonomous orchestration, then application-driven interfacing, and mechanisms for smart, adaptive, and efficient resource management. With community involvement, and of course, we want to be compatible with products. At the bottom, you can see the 3 areas of use cases that we have adopted in order to verify our concepts and also what we will develop. First is in the area of real-time holographic applications, then immersive virtual training, and finally mixed reality interactive applications. And you can find more details about the project at the project webpage. Just a quick look at the partners in the Charity consortium and where they come from. Okay, then let's move on with physics. The project title is Optimized Hybrid Space-Time Service Continuum in Function as a Service. It's again an easy funded project, as I said before. It started the same time as Charity in January last year and will run until the end of next year. The main goal of physics is to unlock the potential of function as a service paradigm through a vertical solution that will enable 3 stakeholder groups: application developers, platform owners, but also infrastructure providers. And with the goal to ease application development and maximize the productivity through the reuse of ready-made abstracted programming flows while incorporating the function as a service approach in the application. Okay, again, here you have the URL for more information about the physics project. And as well for physics, brief look at the partners that participate in physics. Okay, and then some last thoughts about things that both projects have in common, but yet complement each other quite well, as I said. So both projects have the goal to improve the ability of application developers and service providers to create and deploy advanced application for the cloud-to-edge continuum. Charity has its focus on the XR applications, as I said before, while physics on the serverless function as a service type applications. I don't think I need to explain XR, so it's the combination or mirroring of the physical world with or into the digital world. So I guess that's clear. Function as a service for the experts, definitely well known. For some, maybe not yet. It's a serverless way to run applications. It makes life for the application developer a bit more easy, more convenient, because the developer does not need to worry about defining the running infrastructure. And the payment is only for the functions that are actually run. The function itself are defined in workflows and then are activated through an event manager. So quite convenient. Then on the second thing, both projects offer facilities to application developers. In Charity, we provide an environment in which we facilitate the composition of application blueprints. And we specify component microservices, resource slices, virtual links, and that is all being done in a Tosca template. And with these templates, they are ready to run for the orchestrator in order to provide the service and also to manage the service through its life cycle. Physics, in turn, offers a design environment for designing the services by means of a graphically created abstract annotated workflow composite application. And then these are later translated by the platform into FAS sequences in DevOps chain, allowing also the local pre-deployment functional testing. So the application developer can, before actual deployment, see and test how the service is working and everything is working fine. And finally, to mention, both projects provide an advanced lifecycle management of the deployed application, which I think is important for any type of application. But of course, in particular for those applications where the requirements, KPIs and load, etc., do fluctuate over the time the service is running. So therefore, this is of course also a very critical aspect and feature that you need to have for applications, and in particular also for the XR and Charity, I can say this is an important feature that you simply need to have. Okay, with that, I hope I could give some idea of what both projects are doing and the areas on which they work. And with that, I conclude this introduction. We now we'll continue with the sequence of presentation, which I again have put here. And yeah, the next presentation will be given by Tarek Taleb, and he will give the project overview of the charity project. Okay, Tarek, the floor is yours.
I'm sharing my screen. Can you please confirm that you see it?
Yes, we see your screen and we can hear you as well.
Excellent. Okay, so I'm Tariq Talib. I'm actually the technical manager of the charity project. And today I would like to give a very high level overview of the charity project and basically the research questions that we've been trying to address and we are still actually addressing. Well, these are actually the high level 5 objectives of the project. In short, what we're trying to do in charity is to automate the orchestration of both the network and cloud resources. And that's particularly to support advanced media solutions. And here actually we are referring to XR services that are actually well characterized by being highly interactive and quite intensive in terms of bandwidth and latency sensitivity. And of course, another objective of the project is to provide a framework that can help in the lifecycle management of the XR applications once they are running on these cloud platforms. And I believe about this objective, which is here written as objective number 3, my colleague Pablo will give more insights. Uwe has already mentioned the consortium of charity. It's actually, it consists of 15 partners representing 10 different European countries. And we have partners with expertise in telco domain, in cloud domain, as well as in the area of developing XR applications and software themselves. The work is organized in 6 work packages. Of course, I'm not going to bother you with all the details about each work package, but from the title, you can tell what each work package is doing. But basically, we have 2 main technical work packages. Work package 2, which is about the orchestration of the cloud and network resources to support XR services. And work package 3 is the second technical work package, which is about how to make this XR application, how to design them in a cloud native manner, and also how to make them adaptive to the changing dynamics of the cloud as well as the network. We have actually 7 use cases in charity. And they are actually categorized in these 3 high-level categories. So the first one is about holographic applications. It's basically holographic meeting, holographic concerts. Second one is about using XR in the training arena. So we have VR medical training and also software which can help one to create a virtual reality of certain environment, touristic environment. And then we have the third category, which is about mixed reality, interactive applications. And there it's about collaborative mixed reality, with mobile gaming, and also how we can leverage XR to help, for example, pilots or to train pilots. So these are just some snapshots of the use cases that we have in charity. For example, we have a partner that is providing the software for training medical students to operate on, for example, knee surgery in a virtual environment. And of course, the objective of the project is to help this use case to run on the cloud. We have another use case, which is about training pilots, basically how to fly in airplane and the different scenarios and in a virtual reality fashion. And then we have another use case, which is about providing the software to, let's say, content producers or to municipalities, so they can provide, or so they can actually create a virtual environment of certain touristic site. And then we have also another use case, which is about how we can scan the environment and then create a model of that environment and then mix it so we can enable mobile gaming, particularly augmented reality. So in order to support these kind of use cases, we've been actually looking into how the architecture of Charity should look like so we can support this kind of services. And here I'm showing just a very high level Charity architecture, which consists of 3 planes, and I'll explain the logic behind it. So basically, let's say that we have an XR application provider or developer that wants to launch its service on the cloud. And since we talk about edge here, so it can be edge, it can be centralized cloud. So the first point it connects to is what we call the XR service end-to-end conducting plane. And this plane has the intelligence to decide, for example, which cloud domains it should contact. So it will schedule resources and then deploy the microservices of that XR service. And as you can see here, multiple domains could be involved. So these domains could be administratively different, or they could be technologically different. And of course, the communication among them, and also the orchestration, the individual orchestration of their resources are some research problems that we've been looking into. So for each domain, we assume that we have a plane which is specific to that domain, which does actually the monitoring of the XR service. And based on that monitoring, it reacts and decides, for example, how to shuffle resources or how to migrate services and so on and so forth. So these are actually the 3 planes that we consider in the Charity architecture. And of course, if we want to go into a little bit more details, then the architecture looks more like this. Of course, I'm not going to bother you with all the details about each component. But what I would like to highlight here is that actually this architecture design that we have here has been the outcome of extensive study of different architectural work, as well as different standards which are actually of relevance to Charity. Here I would mention ETSI NAV standards and also ETSI ZSM standards. So we try to leverage different standards as well as different research work to, and basically the outcome of that study is what you see here. Given the time limitation, as I said, I cannot go into details about each component, but if you are interested, there is already a paper about this architecture, which details the role of each component and also the interaction among all of them. We have also studied the feasibility of the Charity architecture by basically investigating the different open sources that could be used for each component. So we can achieve the design goals of the architecture. Now, since the topic of this webinar is about opening up the cloud edge continuum to basically media applications, and here in the context of Charity about XR services, so basically here I just would like to highlight some of the research problems that we've been working on. We assume that we have different clouds. These clouds could be at the far edge or the near edge, or they could be centralized, but they could be also operated by different operators, basically owned by different administrators. Kubernetes is gaining lots of momentum, and we think that it has proven that it has big future. So that's why we consider in most of the research work that we do, as well as in the implementation work that we do, we seriously consider Kubernetes as an important solution for our orchestration system. Objective is to basically design, let's say that we have a blueprint of an application and we want to place its microservices on the right environment, and also allocating for it, the right resources, so we can achieve, or we can meet, its requirements in terms of quality of experience or quality of service. And one way to go is basically to create one huge cluster of Kubernetes, for example, that could span across these different clouds. And then this huge Kubernetes cluster could be hosting, these different XR applications. And here I'm showing like a slot of resources, which could be for the development, and another slot of resources that could be for testing, another one for production. So it could be the same huge Kubernetes cluster, which is hosting, all these different applications, here XR applications. So that's actually one, let's say, one school of thoughts. Of course, it has drawbacks and it has also advantages. Another option that we've been considering is basically to create a cluster which is dedicated for one particular application, with all of its DevOps features. So it could be that we could be having multiple clusters, and each cluster is dedicated for for an XR application. Or we could go even further and we could create, several Kubernetes clusters, and each cluster is actually for either the development or the testing or the production part of that application. Of course, each option has pros and cons, and the point is which one to go for. This is something which we are still, we have some ideas about which way to go, but it's not something which is, let's say, finalized. Now, even if we go for, multiple clusters that will be hosting one particular application, there are still lots of research problems that we've been trying to address. For example, how we can autonomously create and manage these clusters. So basically, you can do the manual management of few clusters, but when the number increases or when you have to dynamically change them, then definitely you need to automate the management of these XR clusters. Since these clusters could span across multiple cloud domains, so how we can automate the connectivity among them, or you could have, the same XR application which consists of multiple microservice components which could be sitting on different clouds. So how you can automate the connectivity among them. How to intelligently place these XR microservices and manage their life cycle. Also, sometimes things could change. Resources could become scarce, or just hardware could fail, and you need to reshuffle resources. So how you can reshuffle these resources in a timely manner, how you migrate the services. So these are actually some of the questions that we have actually been addressing. For some we found solutions, for others we're still working on. Since we want to launch these XR applications on, for example, Kubernetes clusters, we have been putting lots of efforts in how we can achieve cloud nativeness in the design of the XR service themselves, how we can make them adaptive to the dynamics of the cloud and the network, and also how we can incorporate these DevOps principles in the XR service management itself. As I said, these are some of the research problems that we've been addressing. We have found solutions to some, with others we are still struggling, but the solutions that we have found, you could actually find them in the deliverables of the project. For example, deliverable 2.1, which is, in my humble opinion, already published, and deliverable 3.1, which is going to become public sometime soon. Regarding the last point, which is how to incorporate DevOps principles in the XR service management, so we can actually enable this XR application management. And this actually, from the architecture perspective, it will be relating to these two components that you have on the architecture, which is the XR service exposure to the developers, as well as to this pipeline for DevOps. These are actually points which relate to the talk which will be given by my colleague Pablo. And unless you have questions, probably we can go ahead and listen to Pablo. Thank you for your attention.
Thank you, Tariq, for the good presentation. I think looking at the watch, we should move forward directly with the next presentation. Again, everyone is invited to put questions in the chat. So if you want to know anything, please put it there. And we will.
And sorry, I didn't I didn't turn on my video, but this is how I look like.
Thanks, Tariq. Okay, then let's move on with the next presentation. That will give an introduction and demo of the application management framework. I guess, Paolo, you are going to start. So anyway, the floor is yours.
Hi, this is Marco Di Girolamo. I will just give a very quick introduction to the content of this next session, that is the application management framework, before handing over to Paolo for a deeper insight. So, as we said, Charity as well as physics are willing to address and serve a class of application developers who have to tackle with quite complex applications and applications having to cope with complex problems when running as workloads in their operational environments. So we want to create best possible facilitations for them in order to help them turn these applications that as legacy are very often monolithic, not really cloud native, not ready to be decomposed in microservices, and take the major advantage of what platforms like Charity or physics can offer. So the application management framework is the module in Charity willing to create this bridge between the XR application developers and the services that the Charity platform can offer. As you can see from the picture, it is composed by 3 submodules. So one is a functional module named XR Service Exposure. That is basically the functionality that we offer to XR application developers in order to build up their application and generates their blueprint templates that are then stored in one of the 2 repositories that we have, the blueprint templates repository, and we also have a service enabler repository that hosts the services and advanced functionalities that the Charity platform itself can offer to its end consumers that are the XR application developers. So we have this friendly editing environment leading the application developer to build up its abstract model of application with the decomposition in the functional elements and the virtual or abstract links interconnecting these micro components. And we will see this much better in the next presentation and the live demonstration. And a point that I like to underline is Charity, as Tariq anticipated, is going with the first prototype at least to use as a virtualization layer and deployment layer Kubernetes-based architecture. But Charity has the ambition to become something more than a project just supporting Kubernetes, because in the future, we might have the need, the opportunity, or the chance to support different virtualization layers. And Charity wants to be open to this, to be more flexible. And so we designed this part of the system in order to separate the general abstract definition of the application from the knowledge, the awareness of the deployment environment where it will be virtualized and executed. And for this reason, the application management framework, once the general application blueprint has been specified and stored, once deployment of this application is triggered, it generates a description of the application in Tosca language. Tosca is a kind of de facto standard in the service orchestration arena. and is a general kind of description that is not bound to the specific virtualization and deployment environment where it's going to be executed. So we create this Tosca specification, and then we pass it to the orchestration layer that translates it into the specific syntax of Kubernetes at the moment, or any other virtualization manager that we might support in future versions or evolutions. And this is how we try to be as general and extensible as possible, serving even better the audience of application providers that we want to address. With this, I would stop and hand over the floor to Paolo for a deeper insight into the application management framework and a live demonstration of it.
Thank you, Marco. Before diving into demonstration, let's introduce the AMF. It is a framework for developers of XR applications, allowing to define application blueprints for the deployment of composable applications in an edge cloud environment. The building blocks of the application are images, and the developer uses the AMF to upload them in a dedicated repository, to select them while editing an application blueprint, and to define additional information that helps the deployment phase into runtime environments. At deploy time, the AMF generates a Tosca representation of the application. Tosca, as Marco mentioned, is an extensible domain-specific language defined by Oasis, created for defining cloud applications. The blueprint editor models applications according to a standard defined by the European Telecommunication Standard Institute, where an application is represented as a network service composed by a set of virtual network functions. Each VNF provides connection points and communicates via virtual links. VNFs and virtual links can be qualified by properties defining, for example, input parameters or environment variables or quality of service properties. All this information is used at deployment time and runtime to decide the placement of the components and to verify the SLAs. Now that we define how an application is modeled, let's have a look at the life cycle of a charity application. Obviously, everything starts with the development of the application. We have a developer that is developing code for the components of its application. And for each component, he will package them into an image. So far, the developer has worked in his local environment, and once he has the images available, he can start interacting with the AMF framework. First, he can upload the images to the Charity XR Service Enabler repository, so that they will be available there for selecting them while editing a blueprint for the application composition. Then the developer can access the blueprint template editor in order to define the application model. He will select from the available VNF images a set of them, the ones that he wants to put into his application. And for each of them, he can qualify additional properties. He can, as an example, define input parameters or environment variables that are required at runtime. He can also define deployment hints to say, for example, that a specific service must be run on a cloud node, while another one can be run on an edge node. He will define the connection links between the services. And finally, he will specify, if needed, quality of service information, quality of service requirements for every communication link. Once he finishes defining all this information, the editor will provide also a visual representation of all these components, virtual links, connection points, and virtual network functions. And the model is ready to be deployed on an orchestration layer. The deployment may happen by clicking on a button on an interface manually or even programmatically. But what happens behind the scene is that the application model is translated into a Tosca model, as Marco mentioned, And this Tosca model is sent to the charity orchestration layer. This layer, based on information contained in the application model, will take some decisions and will decide where to place the components of the application, where to run them. He will select the proper runtimes, and as an example, he might decide that some components of the application may be run on a public cloud in UK, and other components may be run on an edge node in Italy, for a user which is located in, let's say, in Croatia. Once the application is up and running, also a monitoring framework is enabled and a lot of information is collected. Some information is also related to the communication links of the services. And if a quality of services that was defined in the application model is not satisfied anymore, the orchestration layer may decide to change the placement of the components. As an example, he can change the topology of the deployment and put some components in an Azure cloud in Central Europe and other ones in an edge node in Eastern Europe. Okay, let's see now how we can define an application with the Blueprint editor. We consider a simple example, an online collaborative gaming application where the users can join a game for their devices. From their devices, sorry. The main components are a game server that communicates with the player's devices and a mesh merge server, which is used by the game server to get enriched data for extended reality. The previous diagram can be represented in this way in terms of network service specification. We have an external device and two virtual network functions, each of them providing a set of connection points connected by virtual links. For the VNS and for the device, we can specify input parameters, as an example, location or name, while for the virtual links, we can set required values for bandwidth or latency. Now, let's see how all these can be set via a live demo of the editor. Obviously, the entry point to the editor is the login mask, and we can log in into the system with the user which has a developer profile. We land on a very simple page which just offers two main functionalities. The first one allows to manage virtual network function images. The second one to manage blueprints. If we click on the image management functionality, we can see that the tool lists a set of images that are available to the developer. This means that the developer has formerly uploaded such artifacts to the XR Service Enabler repository. Let's say that a developer has just developed a new component and has produced locally an image for it, and he wants to upload it to the XR Service repository. He can click on this button, and by filling in this form, name and tag, by filling in some informational parameter, he can get a command that he can use in his local environment to push this image into the XR Service Enabler repository so that it will be made available to the platform in order to be used in the composition, in the definition of a composable application from the Blueprint editor. Now let's get back to the Blueprint templates functionalities. The landing page is a page that shows all the templates that are available to the developer. This means that he already has produced some templates, and from this page he can select them. He can edit, modify, or deploy them, or even delete. Or he can also create a new one. If we click on the Add New Blueprint template, we are asked for a name. Upon confirmation, the tool shows up an area with four main, let's say, section that we can fulfill in order to define our composable application. The first section is informational, where we can set the name of the service and the version and the description. And the other ones are one for defining external devices that can be connected to the application, virtual network functions that compose the business logic of the application, and virtual links that are the connection links between all the virtual network functions and the external devices. Now, we will not go into the editing of a new blueprint because it is somehow time-consuming, but we can see how we modeled the application related to the collaborative gaming that we have shown in the previous slide with the editor. So, regarding the informational part, we have defined the name of the game and the version, and that's it. The interesting part is more in the other sections of the UI. We had defined the external device. If you remember, we had a gamer device, and here we define this name external device, and we modeled the connection points for this gamer device. We defined an input port and an output port with related numbers, which specify how the gamer device is exposing communication points to the other components. Then we have defined the virtual network function section. We had two VNF, the game server VNF and the mesh merge VNF. Regarding the game server VNF, we have defined first the image name and tag that we want to use from the XR service enabled repository. And the type of image is a Kubernetes pod. And here in the deployment hint area, we say that we prefer that during the placement, an edge node is used for the deployment of this component. Then we define the connection points of this VNF, where we have an input port, an output port, and a port which is used to communicate with the mesh merge VNF. We also require that this component get an input parameter name at runtime that is named GSX. Just an example. Then we define the other VNF, the mesh merge. Again, we define the image and tag name, and we say in this case that we prefer it to be run on a cloud node. Maybe because it is quite resource consuming, and we think that an edge node might not satisfy the hardware resources that are required to provide the service in a proper way. And here we define the connection point that is required by this component to communicate to the external world. Finally, after defining the VNF, we define the virtual links connecting them. The first virtual link, as we can see from this drop-down multi-select box, is a link that is connecting the gamer device output to the game server input. After defining this communication link, we also can specify some quality of service requirement. As an example, here we are saying that we want a maximum latency not more than 1 second. In the same way, we specify the other virtual links. Here we specify that we have a link between the game server and the mesh merge server. And finally, the last link, we define the gamer device input is connected to the game server output. Okay, in this way, we have modeled all the components that we have seen in the previous slide. And we can also see that these components are represented in a graphical way by the editor, where in the purple area, we see the components that are external to Charity. We have the gamer device, which is not managed by the charity framework, while the yellow area comprise all the components that are managed by charity. So we have the game server VNF, the mesh merge VNF, and all the related virtual links. Once we have modeled the application template, the next step would be the deployment request. And the deployment, as we mentioned, would send to an orchestration layer a Tosca model generated for the application. From the editor, we can have an overview of the Tosca model generated. And here we can see what the tool generates and what will be sent to the orchestration layer. Here we can see that all the parameters that are defined here are the ones that we defined in the editor. But in particular, what is worth mentioning is that we are importing in the Tosca model a custom type set, which we had to define in order to model some specific requirements of the charity platform. This is perfectly legal because Tosca is made this way. It allows for customization and extensions with the addition of new types. Okay, this concludes the live demo of the editor. Now we can get back to the slide set. And I will give just a quick overview of the architecture of the AMF. The AMF is composed by an authentication and authorization layer on top, which is the one that we used to log into the framework. And this authorization layer is implemented leveraging the key clock framework. It is a tool that is a very widely used one also at enterprise level, because it allows for very fine-grained settings regarding to authorization and authentication. Then we have the portal, which is a web application developed mostly in AngularJS, but can be extended with any HTML5-based technology. We have the XR service exposure repository, which contains the images uploaded by the developers, which is implemented by integrating with the Harbor container image registry, which is also a very widely used open source tool for managing container images. We have a blueprint template repository, which is implemented by integrating a MongoDB instance. And finally, we have a set of backend services, indeed microservices, implemented via Spring Boot technologies or Python, that are the ones that provide data to the upper layer. While developing the AMF framework, we followed the micro front-end approach. This means that the web application that we can see on the right-hand side of the slide is accessed via a browser, and from the end user perspective is seen as a seamless application. But indeed, every area of the interface is provided by different applications running on different application servers. This allows to isolate the scope of every area of the user interface, and it allows to have different project development teams developing contents for a specific area of the application in an independent way. This is a very flexible pattern that reduces the times for integration and allows for high, let's say, extensibility of the application. The micro front-end approach was implemented by using some technologies, open source technologies, like Webpack 5, and in particular a module called Module Federation, which allows to bundle web applications into components that can be independently run and shown on web interfaces. This concludes my presentation. I hope you found it interesting, and I leave the floor now to our colleagues from physics.
Thank you very much, Paolo and Marco. Very interesting. We are running a little bit late, so I would suggest that we immediately move on with the physics project overview. And Fabrizio, the floor is yours.
Hello, can you hear me?
Yes, we can hear you.
Okay, let me. Lost the button. Can you stop the presentation, please? Because I can't share anything right now.
Okay.
Function. Okay, good. Fabrizio is at the bottom. And I think, Marco, this question is for you. Marco, can you hear me? Are you there?
Yes, I'm here, Uwe.
Yeah, so the question was, how is the location attribute that is utilized? How is it utilized in the charity platform, and what is the purpose?
I would hand over this answer to Paolo, if you don't mind.
Yeah, sure, that's fine.
Okay. The location is an information that might be relevant if we want a deployment to respect some, let's say, requirement in terms of distance to the end users. I mean, if we consider the location of the end user in the deployment strategy, we can ask the orchestration layer to place the component more close to the end user. So in an edge location, as an example, close to the user, so that the user experience would be improved.
Okay.
The main reason for this is the proximity of the deployment to the end user.
Okay, I think that's pretty clear now. So, and I see, Fabrizio, you also have started your slide share. Then the floor is yours.
I couldn't make it.
Excellent.
Yes.
Thank you.
I'm really sorry about that, but there was no button for sharing the screen, so I had to go out and it worked out. Okay, perfect. Thanks a lot. Hello to all. My name is Fabrizio Di Perpo. I work for GFT Italia, and I am the coordinator of the physics project. What drove us to propose a project like physics? Let's see the main elements. The challenges is extreme variability of the offers of the cloud providers, and it is really difficult to be oriented around the various proposals. It is also difficult to find the way on the multiple programming languages supported by the platforms. There are limitations on the iteration of function workflows, function management, and reviews, and also difficulty in adapting application code to new paradigm like function as a service. What is the project vision of physics? Physics develops a platform offering a graphical view of the application flow, allowing through drag and drop commands to create pipelines of functions, function as a service, of course. Physics also offers abstractions and application component reuse through an intuitive flow programming approaches, incorporating typical cloud and fast design pattern structures. Physics also offers a global continuum layer where the deployment of functions is fully optimized, organizing multiple application objectives at the same time, multi-cloud and hybrid cloud infrastructures. But let's see a bit what is FaaS. That means ready-to function as a service. It is a serverless way to run applications where you don't have to worry about defining the running infrastructure and where you only pay when functions run. Functions are defined in workflows and are activated through an event manager. Which are physics goals? Physics aims to unlock the potential of the function as a service paradigm through a vertical solution that will enable application developers to design, implement, and deploy advanced FaaS applications through visual flow programming tools, maximizing productivity through the reuse of ready-made FaaS patterns. Also, benefits for platform providers to integrate functionalities to translate workflows into FaaS-specific actionable sequences and optimize the hybrid cloud edge model interplay. And benefits also for cloud service providers to offer competitive and optimized resource management mechanism services through real-time reaction and adaptation for performance improvement. As already told by Uwe, physics is a research innovation action project with a budget of almost 5 million euros, fully funded. The duration of the project is 36 months from January 2021 until December 23. We're right now at the tooth of the project. Partners are from different typologies, 14 of us, like system integrators, technology producers, research centers, and universities. The project plan is this one. Is divided into phases. We are currently almost at the 2/3 of the project. Phase 1 design and phase 2 implementation are completed. A first release of the platform and related pilots have been released, and an internal evaluation has been made. The phase currently running is phase 3 is almost completed as well. Impact analysis where external stakeholders have been involved. The project will end with phase 4 implementation of the second wave that will take into consideration the internal and external evaluation of the first wave. Then phase 5, the final impact analysis. Let's talk a little bit about the 3 pilots that are planned for this project. The first pilot is related to smart agriculture for near real-time greenhouse management. The pilot addresses the following items. Showcase how the FaaS paradigm can facilitate the implementation of many thousands of daily climatic simulation towards improving crop management and yield estimation. Performance improvement in the execution of simulation, including the possibility to execute simulation in near real time. Optimize running costs and automate application management. The second pilot is related to the smart manufacturing. The pilot addresses the following items. Auto deployment of substitute service in the cloud to increase stability and reliability of software services. High confidence quality control to improve the quality of the products and reduce the number of scraps and returns. And the third pilot is related to e-health, personalized monitoring and collective analysis, addressing the following items. Employ the physics way to deploy functions from the design environment flows, addressing machine learning needs on healthcare data. Predictive modeling with exploring benefits of FaaS inference engine in terms of number and volume of requests. And the last is generative modeling experimentation with phenotyping and synthetic data generation. To conclude the presentation, let me share a video that has been presented for the first time at the midterm review, now available on the YouTube platform.
The vision of the physics project is to empower application developers, platform owners, and infrastructure providers. It aims to ease application development and maximize productivity through the reuse of ready-made and abstracted programming flows while incorporating the FAS approach in their application structure, based on user-friendly function flow programming tools. Its goals is to ease application development while maximizing productivity through the reuse of ready-made and abstracted programming flows. It also aims to incorporate the FAS approach in the application structure. Some of the project's measurable targets include the minimization of service creation, configuration and deployment time by 30% and the optimization of the performance cost trade-off by 30%, the creation of 4 or more different test beds interconnected and tested during the project lifetime with more than 8 different and diverse resource offerings, as well as the creation of a marketplace with diverse artifact categories, targeting more than 30 artifacts. As greenhouses require more and more parameters to be set by the grower, the smart agriculture use case will demonstrate a more dynamic, online process to collect data, model constantly optimized parameter setting in the greenhouse. The smart manufacturing use case will demonstrate how to transform manufacturing architectures to serverless architecture, use of the FAS principle and applied semantics to enhance the flexibility and adaptability of modular production lines, as FAS helps in a variety of optimization problems. As the healthcare sector faces the increasing need to monitor and advise patients remotely, the use of technology and contribute to the everyday self-monitoring, collecting and analyzing real-world data. The use case will demonstrate the use of FAS-oriented tools for analyzing the collected data, making them actionable for healthcare decisions. The physics architecture will follow a functional view in which description of each software component and the interactions among them are provided. The architecture provides the structuring principles that will drive the integration of the physics components in a unified platform. It is expected that the physics architecture will drive integration activities towards producing the physics platform and integrating the use cases. The physics project aims at delivering a complete vertical solution which will offer an advanced cloud application design environments for application developers. In this design, the platform-level functionalities are expected to be easily incorporated by providers, while provider local resource management mechanisms in place will enable providers to offer competitive and optimized services with extended interfaces offering local fine-grained control of elasticity rules and policies. The partners involved in the physics project are leading academic, research and industrial players from all across Europe. To stay up to date on the project activities and results, don't forget to follow us on social media and visit our website at physics-fast.eu.
So this was the last contribution. So thank you very much for your attention.
Thank you very much, Fabrizio. Then we can move on with the last presentation for today. And this one will be given by George Koloris, and he will give an introduction and also a demo of the design environment that is used in physics. So, George, the floor is yours.
Hi all. Can you hear me?
Yes, we can see you, we can hear you.
We are here also with some students of Harkopi University. So we have also a physical participation.
Excellent. Nice.
7 people. They are candidate PhDs, students. I'll send you photos afterwards. So let's start sharing. Okay. So I will be presenting the physics design environment. This is joint work from partners GFT, HPE, and Harkopi University. As Fabrizio mentioned, the project is centered around FAS. So what is FAS? It's a kind of development and execution paradigm in which application logic is split into small chunks or functions. These functions should ideally be stateless or not handle any internal state calls. The function execution is performed typically through a containerized artifact that is easily deployed and executed on top of, let's say, containerized infrastructures. And it's only executed upon request, so no idle time utilization. It can be triggered by external events, cron jobs, or called by other functions, etc. Application logic is typically included in workflows or function choreographies, and the costs are based only on the actual execution time, meaning the number of invocations, the time each function actually executes, with a set price, which is based on the memory used for each function. You can see an example of the OpenWhisk architecture here and what are the intermediate components that are used. So the goal of the physics design environment is to enable a more abstracted and enriched fast application creation. So initially we start out with features about customizing the function environment. So what if the developer wants to add the dependencies like TensorFlow, for example, or other frameworks that are of interest. Then we proceed with the ability to create much more complex function workflows. You can see in the left here the way the Google Cloud Functions workflows are defined. So they are typically in a YML file. Obviously, it's very difficult to scale in a large number of functions with complex links between them, join operations, and so on. Whereas a visual manner would be much more user-friendly and scalable in terms of number of functions in a workflow. Also, the aim is to exploit reusable patterns. We have some examples afterwards about what we consider as a pattern and how this can speed up and augment the application workflow creation. To increase the semantics of the developer directives towards the platform of the infrastructure layers, and to abstract the whole process of packaging, testing, and deployment on one or more FAS clusters. In terms of baseline technologies, we use primarily Node-RED as the main function editor and workflow editor environment. So Node-RED is an open source tool. It was initially driven by IBM. It's a programming environment for event-driven applications. It has a lot of built-in nodes in order to do some, let's say, typical tasks. It has custom function nodes. One can include their own code. And also it has some other nice features like the ability to create subflows or group of functions as nodes, which is easy, let's say, to abstract the operation of a specific subflow. What is more important is that it has a combined nature of both function execution as a runtime and the workflow orchestration. So you can also create functions in the environment, but also dictate logic through which the functions call each other and continue and augment the business logic. So in the case of physics, we use it also as an execution runtime for these functions, as well as a function choreographer for the overall application workflow. With relation to the main FAS platform, we use OpenWhisk, which is an open source FAS platform, again, supported by IBM. It's the main tool behind the IBM Cloud Function Service. And one of the main features that we exploit is the fact that it can execute functions based on custom container images, provided that one abides by the specific interface defined by OpenWhisk. In terms of the physics design environment, the function artifact creation lifecycle, so it comprises of two parts. One is the local part. This is run at the developer side. It consists of 3 different containers that are spawned by a relevant compose file. These containers include initially a web interface through which the developer can control many parts of the process. The main part of the editing is done at the Node-RED container side. This is a local container that is also enriched with the physics provided patterns and annotators in the palette. And the serverless function generator component that is responsible for contacting with the backend cloud environment that hosts the majority of the services. So when the developer starts and creates their flows inside the Node-RED environment, at some point they need to finish and to create a deployable function. In that case, they trigger the building process. The building process pushes the local data to the central repository. The central repository, which is based on GOGs, the central repository also the SFG uploads the flows to relevant buckets, and it triggers pipelines based on the Jenkins CI/CD tool that undertakes the building of the actual image. Once the image is built, it's then uploaded to the project registry, which is based on Carbon. So let's go to the design environment demo. There is a full video available at this link that we can also see. Page. So this is the landing screen, let's say, the admin panel, the main builds page. Here is all my functions, all my flows that I have created. You'll see that the tick next to it is the ones that are actually built. If I drop down, I will see all my build history with relation to what is the name of the resulting function, when it was created, as well as the image that has resulted from this function. So if I want to create a new function, I can go to the Node-RED container tab. And in this case, I can see my environment that has the typical, let's say, Node-RED built-in functions. And then it has also been enriched with a number of physics additions in terms of helper flows. So if you want to do async operations or convert a polling to a pushing process, and the part with the physics patterns, we'll see more about that. And the part about physics annotators, about annotating my flow with specific functionalities. So if I want to start, what I basically need to do is to go and check the OpenWhisk skeleton. This is the skeleton interface that any flow needs to abide by in order to be executed by OpenWhisk. So it needs to have, for example, two REST post endpoints, one with any initialization actions if needed, and the one with the actual execution of the flow. So once an external event comes to the OpenWhisk platform, it will trigger this run endpoint, and it will actually say execute whatever is in this function, or it will actually trigger the execution of this flow. So we go to one of the functions we have. We have already created one. So I can go and, of course, I can augment this and put more complicated function workflow. And then when I go to build the specific function, or rebuild in this case, what is done is that the Jenkins pipeline in the backend is triggered. We will see in a while the relevant link here that we can follow. So inside the Jenkins pipeline, we have 4 different pipelines. At the moment, 2 are completed. The rationale of the pipeline is that we have one initial stage. This is used to generate the specific image. So what it does in this case is that it starts from a baseline. It has a number of stages. So it starts from So we start from checking the differences. We go afterwards to starting from a baseline template. And from this baseline template, we add any differences that are done inside the developer branch, let's say. So this might include installing new dependencies I have added in my noded environment here. If I have added any new nodes and so on, all these are installed in this part. So this takes a while, so we can go and see previous one that has finished. What is the output of this stage is actually a Docker image, and this Docker image is pushed to our registry, and it's ready to be deployed. The deployment, it happens initially on a test facility. The test facility is, let's say, kind of a local environment that is used for testing. And this specific facility, the second pipeline gets that base image and registers it as a new OpenWhisk action. This is a different pipeline. So it basically triggers the OpenWhisk action creation API, and it registers a new action using the specific image that was generated in the previous part. So after I have done that, I can go in and through this process, I can also see logs from the involved backend services, which are very helpful for debugging and also seeing other cases of errors. Once I have built something, I can go and test it directly to the environment. And then I can wait for the execution to finish. So now I'm invoking through the OpenWhisk API. OpenWhisk triggers the execution of a relevant container that is based on the image that has been mapped to that function, and I get the result in the specific case. Also through the logs, we can see also the logs internally of the container that actually executed my action. Other parts of the design environments is also the ability to create graphs. So by graphs, we mean basically collections of flows that are handled by the framework as one bundle. This means they are deployed at the same time, and also it means that any optimization, any locality consideration, any other case is applied at the application level, which includes these one or more flows. Slideshow. This, but okay, let's see now some how the eHealth system, for example, utilizes this case. So the main scope is at this stage to migrate the model inference to a fast-based execution. So the Healthendia system gets data from smartwatches or relevant devices with patient, let's say, vital signs. And then at some point in time, these can be passed to the ML model that is responsible for detecting the state of a patient. So in this case, the execution is more dynamic through physics in the sense that it can be triggered whenever the new update from the user gets in, then a relevant function can be executed in order to estimate the patient condition. In order to do that, the eHealth model inference starts out by creating their own version of the Docker file. So each developer that comes into the system gets a clone of the, let's say, of the template repository, the master repository, but then they are able to, in their own branch, to create differentiations of their Docker file, their Jenkins file, and so on. So in that case, the eHealth use case needs to change the Docker file in order to add, for example, Python and TensorFlow tools inside the image. Then they need to add also their own custom Python script for doing the model inference process. And then they need to create a flow that actually adapts the execution to the OpenWhisk interface. So we see again the OpenWhisk skeleton interface and a couple of preparatory functions, then the execution of the main Python script, joining the result of standard output and standard error, and preparing the response to be given back to OpenWhisk and to the user. Also, they have the ability to test locally inside the Node-RED server. This is very important in order to save time. So you can see here some statistics from the relevant adaptation. So from approximately 10 errors that we had during the adaptation of a similar flow, 7 of them were able to be resolved within the Node-RED server itself. So without actually having to build, deploy, etc. Building and deploying means around 5 minutes of time. So with the ability to manually invoke inside the Node-RED server case, we are able to save this amount of time in approximately 7% of the cases. Of course, then we might have also to do deployments on the FAS, actual FAS platform, because we also have some errors there. And in the end, to add semantics, the specific semantics that are added are with relation to sizing consideration that the developer wants to add, the execution mode. So if they want this flow to be executed as a service or as a function, and other considerations like locality. So if we have a number of available clusters, the developer could dictate that the specific flow should be deployed on a given location. And we have a number of other annotations with relation to optimization goals if we want to optimize performance, energy, etc. In terms of the patterns we mentioned, as I showed in the palette, initial palette that the developer starts out, they have a part that is about the physics patterns. So as patterns, we define, let's say, groups of functions, group of functionality that can be reused. So it's built in a parametric and reusable manner. The idea is that you can drag and drop these functionalities and create faster and more complicated flows. So we have patterns with relation to parallelization. I will show an example afterwards. We have patterns related to context management. So when containers are executed in the FAS platform, the first invocation might find a blank container. The second invocation might reuse the previous container. So what happens to the context that is there from the first one? We have, let's say, structures that are able to either maintain this previous context or delete it, depending on the use case of the specific function and whether one favors, for example, performance versus security and so on. We have patterns related to data collection. So how can you have ready-made flows that are used for data collection with enhanced reliability considerations, being able to handle network outages and pushing the data from the edge to the central cloud storage. We have patterns with relation to request management and workflow primitives in order to assist developers into better creating, let's say, flows that are have complex joins and have correct compilations of the message flows. As an example of the parallelization patterns, one we have implemented is the fork join one. So how can you get an initial, let's say, load? This load is then split across different containers. It uses many different functions that we executed, and then the result in the end is joined and then forward to the remaining workflow. So in this case, you can see as an example, we start out with a concept. So how the concept of fork join is mapped to the event-driven function-oriented paradigm. So we consider having an array input. This array input is then split into individual messages, one per row, for example, or one per multiple rows, depending on the split size. Then a fast invoker gets its message and does an invocation towards the fast platform. This results in having n parallel containers. And then in the end, the join function joins the operations, the results of all the containers. So starting from that, we implement it as a subflow. So you see it's quite complicated, but the user doesn't have to know anything about it. They can just drag and drop it and utilize it inside an ordered flow that can also in turn be executed as a function. So you can have function orchestrators, either like server flows or like functions. And the only thing the developer needs to do in this case is to parameterize the pattern node with relation to a number of parameters of configuration, like the split size, what type of execution one wants, whether it wants to be fast or multi-threaded or multi-process inside the same container, what is the inner action to use, and so on. So we have an example of such a demo. So in that case, what we have is a split join pattern around the function. So we will basically trigger the execution of this function with 4 different inputs. We have used a split size of 2. This means that this function will orchestrate the execution of 2 hello world instances. Each instance will undertake printing of 2 of the 4 inputs. And in the end, we'll see the result. So if we go to the panel, so this is the resulting flow. You can see that this has been configured with a split size of 2. And this is the part to trigger directly. This is if I want to test it locally, and this is if I want to invoke directly the function. So what I have basically used a message payload that has these 4 different names and what interaction URL to use and the credentials for that action. So if I trigger that execution, you can see in the backend in the clusters the fact that it has created one function. This function is the SJ multiple function, and this function has spawned 2 other functions about the hello world. So in the end, what I see in my has failed also. We have a bit of a problem with high memory consumption days. So some of the functions fail, but the second time it will be okay. So you see we have the SJ multiple, and then we have the 2 new functions that are invoked by the specific. No, still.
Sorry, Georg, I think we need to conclude on your presentation soon, because we are running out of time.
Okay, so just to mention that we have a beta testing available. So if you are interested in having accounts on the physics platform, just send us an email and we can send you the initial login details and then you can register. Once your account is created, you can download the installation guide, which is basically used in order to configure your local containers. And this is also very interesting for example, for AI serving measurements, we have 3 available sites at Haracopia University and 2 clusters on Amazon and Azure. So anyone that is interested in porting their AI serving, for example, flow and having some results, they are more than welcome to try out the platform. Also, all the artifacts are being published regularly as Node-RED reusable subflows, so you can see them in the following link, and included as artifacts in the project marketplace, along with other physics components like OpenWhisk operators and so on. So thanks all for your attention. Questions?
Thank you, Georg, for this presentation. Yeah, before we open the floor to the audience for question, I have already one question for you. Could you explain what is the benefit of the orchestration in physics compared to other fast platforms? I mean, what do you do better?
Yes, one of the main problems of many platforms, fast platforms, is the fact that in many cases they don't support, let's say, very complex workflow structures. So, for example, OpenWhisk has only sequences. Sequences are okay, but in the end, you cannot implement, for example, the parallelization pattern if you don't have a join operator. So one is this fact. The other is the visual way, as I showed also the case of the Google Cloud Functions. It's based on a textual manner. So it's very difficult for a human to create a large workflow with complex links, with conditions and things like that. And I think that the final benefit is also the fact we mentioned that one can use an Node-RED environment itself to either as an execution runtime or as a choreographer. So if you have, let's say, an orchestration step that goes from, let's say, one function to another, if you execute it in the fast platform, so both functions are deployed on the fast platform, you get much larger delays in terms of, let's say, provisioning the containers. So this function might be actually a very small function, and the largest part of the delay is actually provisioning the container. So in the physics way, you are able to put functions in the same container, and only if you have something that needs very large parallelization to then use multiple external functions. So you can minimize orchestration overheads in the end. You can select which parts are going to be executed inside the same container, or which parts are going to use also other function containers to exploit the parallel.
Okay, thanks, Georg. So we can now open the floor to questions from the audience directly. So are there any questions, any further questions? And you could just speak up. Are there no questions? Does any of the speakers maybe want to make any comment, say anything?
Okay, I have one question. So related to memory, because in the last demo you tried to say that the memory consumption is very high. With associated memory is associated energy consumption, and some of the computation works in the cloud, some on the edge. So what would you like to comment on that?
You mean for the memory of the
user device on which the application is actually running?
Yes, the memory I mentioned was for our test bed, so the test bed is a bit overloaded these days. In general, for the memory part, or for any, let's say, trade-off part, there are some things that are, and based on the feedback we had from the use cases, So they really like some things to be, at very specific places. And the trade-offs then can be made dynamically during runtime. So for example, in the smart manufacturing, they prefer local execution in their own cluster, and only when certain conditions are met to move to cloud environments. In the smart agriculture case, is the opposite. So they only want edge to be used for data collection and the main part of the processing to be done on the cloud, because they want their edge is a kind of a Raspberry Pi device. So they want the ability to run multiple simulations and fast, relatively fast. So they want to go to the cloud. So the issue of which one wants to deploy where is very heavily relying on its use case and the specifics of it.
Because in this latency is critical, so I think it's very important to decide how much and what gets processed on the cloud and on the edge.
Yeah, you're right. So we couldn't fit it in this demo, but we have developed a load generator for us, and this takes a very large number of metrics into consideration. So if you have multiple candidate locations, you can benchmark a function across all locations, and you can actually have very nice results with relation to latency, for example, to wait time in each system, to what system has the best, let's say, hardware resources for the function duration itself. You can see what happens if you have multiple concurrent containers. You can also potentially limit these containers based on the needing higher memory for each one to reduce the concurrency effect and so on.
Thank you.
Thanks, Georg, for answering. Are there further questions? Any further question, any comment? Seems not the case. Then I think we can conclude for today. I mean, first of all, I would like to thank everyone who was helping to organize this webinar, everyone who was not visible today. It's a tremendous work needed in order to prepare and to disseminate, to ensure people community gets aware. So thanks for that, and then of course also thanks for the audience for staying longer than we announced. But I think we heard very interesting presentations, so I guess it was worth the time to stay online. And if you are interested to keep following the activities of the project, please visit the project websites where we have opportunities for you to join our newsletters or the Twitter channel that we have, or follow us, our LinkedIn group, where you at regular times will get up-to-date information about the projects. And as I said before, the video has been the webinar has been videoed, so the video will also be made available, I guess, very soon, and you will find the link also as well on the pages of this webinar on the projects on the web pages of both projects. And with that, I would like again to thank everyone. Have a good evening, and hope to see you soon again at one of our next webinars or at other occasions. Thanks, everyone.
Thank you, everyone.
Thank you.
Nice.